Okay, tonight we have a special guest with us, as some of you have been reading about. And I sort of look forward to his presentation, having bought a new van, and I'm trying to figure out what antennas I need to put on it or take with me, especially to go out here in the hills away from nothing and to be able to communicate in emergencies. And our speaker tonight is well qualified, if not overqualified. As an inventor, Dr. Jack has been creating out-of-the-box antenna designs for over 25 years. He's way ahead of me. His antenna technology is based on his unique three-dimension understanding of electromagnetic waves and their interaction with the world. So at this point, I'd like to turn it over to Dr. Jack. And Dr. Jack, would you go ahead with your presentation?
Absolutely. Well, by recommendation here, if some want to remove their video, that's probably a great idea for bandwidth. And I'll go ahead and do screen sharing now to go to the PowerPoint. Let's establish that that's working well, shall we? I have things pretty much optimized here, and checking to see if you can see the first slide.
Working just fine.
All right. In that case, I'll go to the slideshow so that you can see it full screen. And there we go. And let's see if I can hide that. Very good. Okay, can you see it in full screen now?
Just fine.
Excellent. Thank you, Rosendo, Lloyd, Bill, and everyone else here. And also, I appreciate that you're recording it and are able to find a way to bring it over to YouTube. I think perhaps a lot of members of your club, as well as surrounding clubs, the wonderful state of Texas, and indeed, many other ham radio operators would enjoy and find some enrichment out of the presentation. I'm checking one more parameter here and then I'll proceed. Oh, by the way, this will be about 30 to 40 minutes and then follow up with questions if that sounds good.
That's just fine.
Okay, very good. Do you see the thumbnail video over to the right now is my final question before I proceed? Or is that only me that can see it?
Yeah. I think that's only you.
All right, in that case, I will absolutely reduce it at this juncture. Okay, very good. Well, again, it's very clear, and thanks again. It's COMPACTenna.com. And there's a lot of interesting information there. Certainly not a boring site, I don't think. There are some videos demonstrating the performance, the technology. It's all about small, high-performance antennas. Small, high-performance antennas. Wait a minute, that's an oxymoron, right? Kind of always has been. You reduce the size of the antenna, and all kinds of challenges occur in terms of gain and bandwidth and, well, et cetera, right? So how can we get past that? Well, this is a visionary concept, one of about 15 patents of mine, rather revolutionary, and this one is unique in and of itself, very much focuses on the magnetic, but also the electric field, and we'll talk a little bit about that. So we'll show, and I hope you find this interesting, how there is actually a way to do this, which is wonderful. It's a niche market, but it's a growing niche market, both for mobile environment, for people for VHF, UHF that always wanted to have, you know, even if they could just get reasonable performance from a small antenna in their vehicle, so they could get in and out of their parking garage or through drive-throughs or the hospital parking garage or anything for that matter. But it wasn't really possible. So, you know, we resorted to layover designs and removing the antenna when we would, you know, jumping out of the vehicle, and that was unfortunate. So I propose that we here now have a solution, and let's see if we can talk about it. This slide encompasses everything in a nutshell. I'm going to talk a little bit about the various aspects of this, science. It's not just technology and innovation. It's invention. It's visionary, and that's how it works for me. And then it takes some years in order to bring it to reality. But it comes in nanoseconds generally as I'm awakening, and this one is no different. So here we are now, and I have perfected it in certain applications, but we're going to talk about the science of it, the technology of it on a few slides, and then we're going to get right into the meat of it. So bear with me, and we'll get right into, well, what models do you have? What do they do? What's their size? You know, what frequencies do they cover? But this is it in a nutshell. Let's look at this slide. There are 3 parts, 1, 2, 3. That's what it's all about. And it's kind of pseudo illustrated by the logo. So let's just read it. Unique electromagnetic field diversity, science and technology. So here we go. First part, with a special design construct of spiraled and cylindrical metal sheeting, including what I call the extended flat monofiller spiral Tesla-like coils. Okay, not the bifiller a flat Tesla like style coils, but extended flat monofiller. All right, and they're wide. Okay, so just to jump to the chase here for a moment, it's a sheet of metal that's rolled as such. But this is not a roughly quarter wavelength antenna where you get broader bandwidth, you know, by making it instead of a wire, you make it a wide wire, you know, or a large diameter wire, increase the bandwidth, or make it a sheet, you know, or then take that sheet and give it a various construct, or even roll it. No, it's not that. It's extremely short, 1/6 of 1/4 wavelength kind of thing. All right, and that's all in the patent. So what happens when you do that is you're able to do something very unique. Rather than the matching system, and you always have to have a matching system, because when you shorten an antenna, when you take a monopole, a quarter wave, you shorten it, you bring the high voltage point closer and closer to the ground plane counterpoise. So you know, there's always the resistance, the capacitance, and the inductive components. But the resistive components automatically goes way down, and you have to make up for that. So we get all kinds of different internal or external components of matching circuits, and they can be lossy. That is the first thing I'll say. They can be lossy. So is there another solution? Yes, there is. Make the matching system for the inductance and capacitance efficiently done within the actual physical metallic geometric form of the antenna itself. That's the first thing, okay? So virtually eliminate losses that you get in all the various iterations of internal and external designs that we've seen in the past, with all the drawings and all the mathematics that goes behind it. This is entirely different. So that's the first thing you want to do. And that's the basic way to do it. Now, what happens then? When you do that with this wide monofiller spiral Tesla-like coil, you create what I call the magnetic field resonator. Now, what is that? You know, anytime you have a tank circuit, a capacitor and an inductor in parallel, well, you know, it resonates. You have vibration. You back and forth. It's a tank circuit. Yeah, but it's often very wasted. If instead you have something with a built-in resonating matching system, that's an effectual component of the electromagnetic field production, now you not only have the reduction of the loss of standard antennas, now you also have within that an effectual component of the electromagnetic field production, both near and far field, and we'll get into that a little bit later. Okay, so that I'll spend a little bit more time on this slide and than the others, but that's very, very important. Reduce loss and create greater signal production efficacy. All right, and then lastly, in so doing, with some added geometric construct, what you wind up then having is diverse, or our diverse effective electromagnetic field. Not just effective, but diverse. What does that mean? Well, we know there are various diverse polarization antennas out there. There's single polarization, there's vertical, there's horizontal, you know, there's circular polarization, there's elliptical, and circular is one type of elliptical. This is essentially elliptical polarization, but it's diverse electromagnetic fields. And why is that important? Because most of our communication is in obstructed environments, certainly in the VHF, UHF communication world, you know, within the city, even in rolling hills, up and down, VHF, UHF, and we also get flip-flop of polarization, don't we, with HF communication? Of course we do. Otherwise, a vertical antenna in one state would not do, or country would not do well with a horizontally polarized beam in another country or state, because there's flip-flop constantly of polarizations. So we're fortunate in that way. But here in the VHF UHF world as well, when you have this flip-flop and polarizations, you get a lot of flutter as a result of that. So you have further enhanced the performance in the world of dynamic. It's not just obstructed world, it's dynamically obstructed world, moving vehicles, moving doors, moving people, tree leaves, all kinds of things moving. This mitigates the signal drops. Okay, think about that. You're driving along, you're reducing the signal drops, right? You're reducing the flutter. And what does that actually do? It actually increases the reliable range. Your absolute maximum range with your very, very long 7-foot high gain VHF antenna on the top of your vehicle is going to do a little bit better when you're at extreme ranges and you're hilltopping. But that's the only situation. Short of that, you actually increase what's called reliable range as opposed to maximum occasional range. Okay? And by the way, anybody interrupt at any time if you'd like, or we can always come back to particular slides at the end. All right, let's move on. And all right, so talked about we have to get efficient with the antenna. We have to reduce loss, yes, and we have to create an effectual component, an effectual component of the electromagnetic field. That's right. And then polarization diversity. So let's talk about antenna efficiency. A lot of people think it's just one thing. It's actually more than that. Some will say it's two things. I present to you here, it's four things. All right. First of all, antenna efficiency. We all know SWR. All right. Return loss. You have power forward. You have a certain amount of power coming from your transmitter going towards the antenna, and a certain amount of it reflected back. Yeah, and that's why there's such a great search for the ultimate best SWR. I will propose to you right now that an SWR of 1.7 to 1 on a very effective and efficient antenna is a lot better than an SWR of flat 1 to 1 on a dummy load or an antenna that's essentially that. All right. Now that said, you always check SWR because you know there are certain limitations on transmitters and amplifiers and these kind of things. So yes, but the point is that is part of the efficiency. And at the end of the day, by the way, some of that power reflected, I have to watch I don't take up too much of your time. On the power reflected, some of that comes back to the radio and goes right back. And by the way, it isn't the SWR that hurts the radio. It's the power that comes back, but it's not just the power that comes back. It's that it sets up oscillations. in the final circuitry of the transmitter, and that causes increased current surges, and that causes the damage. But some of it actually reflects back again towards the antenna. You may have found sometimes when you had a higher SWR and you looked at your meter that has both SWR and power, you actually see higher power, and it's like, hey, this is great. Yeah, but my SWR is high. That's what's happening. All right, it's all about cancellation and summation all along the coax, et cetera, et cetera. But in the long run, you eventually wind up with an electromagnetic signal. Okay. Antenna efficiency is also about pattern. You can have a very high gain antenna, but if you're down in a valley in a vehicle or your house or your business or whatever the case may be, and you have an extremely high gain antenna with a very narrow elevation coordinate pattern, you're going to shoot that signal right into the side of the hill. You're actually better with a quarter wave, right? So you know, it's always been a trade-off. What do I do? Mobile? Do I do quarter wave? You know, 5/8 wave, collinear, or let's just leave it, or do I go half wave, kind of in between? I propose to you this is an entirely different solution. All right, so the idea was to create an antenna that was of reasonable performance, yet extremely small. We're going to get to it. It's only 7 inches long, people, for VHF, UHF, and even 220 band on the tri-band. That's all it is. But it's an amazing performer. Thank God. And so the pattern is very important. Heat loss, antenna efficiency, heat loss. You know, the antenna is constructed in and of itself, of its radiator, and also, of course, of its matching system. And if the matching system has heat, well, that's loss. So that's part of the efficiency. And then lastly, this is really important, nor does the capitalization. Field effectiveness of the matching circuit, the system. If your matching circuit is doing a great job, well, great, right? But if some of the energy is used in that coil, or even the capacitor for that matter, in generating some electromagnetic field, and it's wasted, you know, it isn't dissipating, you know, into an effective electromagnetic signal, well, then that system is very poor in its effectiveness. I'm going to stop here for just a moment. How is it coming along? Bill, is it coming along well?
Yes, sorry, I had to unmute. Yes, it's, I'm anxious to see what's coming up next.
Okay, here we go. Great. So let's look at, thank you so much, Lloyd. That was Lloyd, wasn't it?
Yes.
Yeah, thank you so much, Lloyd. All right, so we have the shortened monopole antenna. I'm not going to go into this in detail. I'm sure some of you are reading it already. We have the standard way of doing things, the standard methodologies for matching, and there are variations on the theme, right? You know, we have, you know, we have loading coil, tuning coil. This particular drawing I put together throws everything, including the kitchen sink, in there, right? Virtually anyway. But over here we have this simpler standard methodology. Sometimes we have the loading coil and tuning coil all in one. That's this one, for example, where you have the feed and you have the coil, the inductor, right? And then along that you have the shunt capacitance to ground, just like this kind of thing. So here you've created within your LCR a circuit, you have your inductor and your capacitor in parallel, increasing impedance for a very small impedance. You know, shortened monopoles, oh my goodness, even a full quarter wave monopole with an extensive ground plane counterpoise in all directions around of it, especially if it's flat, and especially if it's even, well, all right, let's just go with that. You know, you're not at 50 ohms anymore. You're already down to 25 ohms with a 2-to-1 SWR. And as you shorten the monopole and the tip gets shorter and shorter to the ground plane counterpoise, your resistance goes down, down, down. You can get down to 10 ohms, 5 ohms, 3 ohms. You know, you have to make up for that for some kind of a matching circuit. And that's very much what all of it is all about. Capacitance hat is kind of nice. It can decrease the length of your your loading coil there, and also help you in terms of overall efficiency and a little spatial diversity as well. But again, I'm going to stop going off into tangents at this juncture. No more detail. We can always do that at another time. So we can have shut capacity. I already discussed that. So what happens with all of this? Okay, and oh, by the way, these circuit equivalent circuit diagrams of antennas. Oh, here we have, of course, the coil. Here is the shunt. The capacitance is from here to ground from the antenna itself. It's actually much more complex than this. And more recent articles in electronics journals and physics journals, some great minds on this kind of thing, and all the affiliated mathematics. It's actually a simple whip is not a simple whip at all. It's kind of like this. Seen this kind of thing before? LC, 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 LC. Sure have. You've seen that in transmission line equivalent circuits. Well, essentially, when you come to the end, the load, you take in your transmission line and you split it. So indeed, this kind of thing occurs. So it gets very fun, very complex, but that's just something that I love to do in my mind. So what happens when you do the standard kind of a thing like this, and you try to beat it with things like capacitant hats and various things, you decrease bandwidth. We all know that. How are you going to make a 7-inch, how are you going to make a 7-inch tall antenna, Dr. Jack, for a VHF and not get decreased bandwidth? Well, remember I talked about the folded sheet? When you go from a wire to a thicker wire to a sheet, you increase bandwidth. That's part of it, okay? Decreased gain. You have decreased gain. Well, you have decreased gain for a lot of the reasons I talked about on the other slide. You have inefficiencies, all 4 different reasons, and I'm combating those. All right. Again, realistically, if you're mountaintop to mountaintop, although atmospheric disturbances do change things at times, but let's discard that for a moment. Gain is everything. But that's not the majority of what happens in the communications world. Certainly not in the land mobile radio communication world, and not even with, and you'll see a slide from a major defense contractor that did not want to be named, but was doing some research on this science and technology. They were amazed and came back. I says, well, remember I told you about such and such? Oh, that's right. All right, you'll see that. So matching circuit inefficiencies, we talked about that already. All right, so what can we do different here? How are we going to construct something? And I've already alluded to it, but let's look at a drawing. This is from the patent itself. This drawing here, you can see the stem, you can see the folded sheet. Listen, there's additional geometric components. I'm not going to divulge everything here, but this is the basics of it, right? So we have magnetic fields in the vertical polarization here, but here, of course, we have it in the horizontally polarization, just like you do of any monopole, stick, whatever. Yeah, and these components, of course, are going to be somewhat out of phase. Right? That's what you have to do. You have to have something out of phase if you want to create polarization diversity. Just like your circularly polarized antenna, which is roughly a quarter wavelength out of phase, the vertical and the horizontal elements, or they're fed, or they're juxtaposed to each other and they're fed a quarter wave out of phase. But one way or another, you have to have the differential in the phase, and that's what this does. That reduces flutter, because the signal in the dynamic obstructed world is creating hot spots, null spots. It's also flip-flopping in polarization, and this is a lot of what causes the flutter. It's irritating. It's actually unsafe. Wouldn't it be a great thing if in the moderate ranges, the extended reliable range, especially like in the city as well, but actually both. What am I saying? Both. It's really important to get a greater reliable communication. So important. This is a drawing that shows the complexities of coil. It's actually much more complex than one might have thought in terms of the inductance, which is of course of the coil, and the interwinding capacitance, the end-to-end capacitance, and the capacitance effect with the metallic sheet below it. Kind of summarized here. Well, so I talked about this already. With the COMPACTenna, though, what's happening is when you have this folded sheet, you get not just a little bit of interwind capacitance, you get a tremendous amount of interwind capacitance. And as Tesla already taught us, and that the inductance that you get from a coil of this nature is of a certain amount per length, but if you wind it in a flat spiral, you get an increased amount of inductance per length. So at the end of the day, you get a tremendous buildup of the inductance and the capacitance, and guess what? It's in parallel. Remember the other slide about matching? You need to get that inductor and the capacitor somehow in some part of the circuit in parallel in order to create the increased, to balance the decreased resistance component. Okay? All right. So what does it actually do? Well, it reduces the flutter that I talked about, and this is just kind of a hand drawing of giving you an example. The red line would be a higher gain antenna. And you know, you're driving along, or you're stationary and the tree leaves are moving, right? Just as one example, right? But at the end of the day, because of the flip-flop of polarization, also the spatial changes, you know, how much of a decrease do you get with when you get that flutter? Well, it's huge. It's 20 to 30 dB. Actually, it'd be 1 over n to the infinity. But frankly, there are other minor reflections going on. But also, if you take, for example, a vertically polarized antenna and you try to communicate with a horizontally polarized antenna, you know, the ARRL handbook tells you that you're down 20 to 30 dB. It would be even more than that, but the physical construct itself makes it impossible to get ultimately of 0 thickness. So, and you have some components of the install. So, you know, you're going to get about 20 to 30 dB down. This is why you often hear about in propagation analysis programs that you want to be at least a fade margin of 15 dB because you need to make up for a lot of that occurs, all right? So what if you had an antenna? Let's theorize the blue line. What about the blue line where the absolute highest gain is just a couple, 1, 2, 3, maybe dB lower than a really long high gain antenna, but the drops are substantially reduced? Well, then what actually happens? This is the minimum signal you need, or signal to noise ratio, in order to maintain the communication. Well, look at this. You're actually above it entirely here. Now, in the real world, there will be circumstances where it will drop below, but you have substantially mitigated the problem. So therefore, in the vast majority of your communications, you actually have a better, more steady, reliable signal on analog. And by the way, whatever you do that improves analog flutter, it dramatically improves digital communications even more so. All right, that has a lot to do with going from packet loss to frame error rate to actually decrease throughput and drop of connectivity. That was a good quick summary. All right, I got to do more of that. This is just another way of showing the same thing. Over here, we have somebody, for example, driving a certain distance away from the repeater or a base station, for example, or another mobile, whatever. And over here, it's the city. So this is kind of a representation of the same thing, the higher gain antenna. Now, basically, you can see if you take that line, that minimum signal to noise ratio, greater than or equal to the noise floor, and you continue to lift it, okay, because the signals are actually dropping down, let's say as you get further away, right? You know, you have more and more of the flutter problem with this higher gain singularly polarized antenna, than you do here. But you will come to a point, notice, you absolutely will come to a point. There will be some of this, and actually there's a little bit of this kind of peaking going on here, where it does just sneak above, it'll just peak above that minimum signal to noise level that you need, and the COMPACtenna will not. All right, but what you wind up with in those extreme distances is your hilltopping. You'll occasionally get it, and you will not with the COMPACtenna, or it'll be very weak. All right, but the vast majority of the time you don't get it at all. That's the only time that the high gain wins in that scenario. Don't get me wrong though, you do a tower to tower, point to point communication, you need gain. Actually, you need diversity as well. You need both because of atmospheric disturbances. That's why, for example, a lot of times you won't see one 12-foot dish up there point to point, but you'll see on the same tower 2 8-foot dishes separated by 30 wavelengths or so, because that actually does a better job. All right, in the city, something really cool occurs because you have both slow and fast flutter. And because of the fast flutter, look what happens here. You have summations and calculations that are cancellations constantly going on with the higher gain antenna, where you overall have a medium signal that's actually lower than the median signal of the COMPACtenna. So driving around the city, it's absolutely amazing. As much as driving it at a moderate distances are really neat and enriching and fun in communications, much less emergency styles. This is really neat in the city, where it's not just peaking above most of the time. You're actually getting a greater signal strength on your S meter, and it has a lot to do with the fast flutter. Slide. Okay, this is from the defense contractor, major defense contractor testing this. They had a full-size monopole. This was in the 20 meter arena, and this was the COMPACtenna, very very short. This was HF COMPACtenna. And now, as you can see, the peaks are higher, right? We have the ionosphere fluctuation, propagation, and polarization fluctuation. So the peaks are higher. 22 versus 13, 14 versus 7.5. Here's the 10 dB microvolt line. But this is what fascinated them. And that was this. When the signals got down to virtually nothing on the high gain full-size monopole, they actually had slight improvement on an antenna that was a fraction of the wavelength, or a fraction of the length, well, wavelength, and a fraction of the length as well. So 1.5 dB up to 3 dB, 8 dB up to 10 dB, 9, 9, 7, and 8. So again, peak signals are of lesser strength with the COMPACtenna, but low signal strengths are mitigated. And this meets a growing need for HF antennas in limited spaces as well, housing associations, homes, etc. So now we're going to just jump right into the model. Okay? Okay, hearing nothing, I'll move on. Here we have the very, very popular 7.5-inch and 9-inch antennas. They look the same, they're just slightly different in length. NMO connector, leaf spring style, doesn't burn. Some of the antennas you'll see NMO have a little spring inside, a little pin with a little spring. Boy, with any reasonable amount of power, especially over any period of communication time, that little spring can burn. A lot of people don't realize it because it's actually the slight weight of the pin that drops down that makes the connection, but it's not a great connection anymore. So I went this route, and I use United States, all the United States tool and die shops and manufacturers, particularly local, but actually all around the country. So we have the 7.5 model, is a 2 meter, 220, and 440. For the 220, I had to add an extra magnetic field resonator for that. The 2 meter 440, for those that don't need 220, want to save a few dollars, looks exactly the same, but on the bottom, instead of having a T for tri-band, it has a D for dual band. The Scan 3 antenna is government optimized and extremely broadbanded. you know, 136 to 174 megahertz in VHF. Wow. 380 to 512, all the government, military, all of that. And the 750 expanded band, the 800 expanded band, it goes all the way from 750 to 960. It covers it all extremely well. It's optimized for that. And by that, by the way, an up and coming thing is GMRS, and it's really good for that. We have two examples. Here we have it on a magnet mount on the on SUV or crossover, and here we have it on a pickup truck. Notice the location. Notice the location, right? A lot of antennas with their matching system and whatnot are designed for the center of the roof, which oftentimes, by the way, because of the moonroofs or sunroofs, you really don't have an expansive ground plane all around it to match that matching system of the standard technology. And they don't match up typically nearly as well at any corner. And there's lots of corners on vehicles. Well, this antenna was actually designed for that. At the end of the day, the matching system of the monofilament Tesla coil magnetic field resonator does match up to improve that resistance component. But by putting it near a corner, it gives it even a little bit boost, because at the end of the day, it's kind of like acting like the downward, like a dipole kind of counterpoise. And because we're dealing with VHF and UHF, you know, we're not dealing here with HF, where the pole, as it were, would be in a certain direction, CB, 10 meter, whatever the case may be. That's not true. Here it's still substantially omnidirectional, utilizing this technique. Now, one may wonder about this magnet mount thing. Okay, that's great. You can put it on any corner. It's very convenient for me, Dr. Jack, but you know, this whole magnet mount, I've often wondered about that. I'm not going to explain this whole slide. I went into even further detail on the calculation of the capacitive coupling with magnetic mounts, okay? Taking into consideration fringe effect and all of that. It's on my website on the installs page. What essentially it boils down to is you're good. With a good magnet mount on VHF, UHF, you're superb. VHF, you're very, very good. Really, things only begin to start being a consideration in the HF world. And if you go to a 5-inch magnet mount from a 3-inch, you're still pretty good, even to 7 megahertz or 40 meters, not at 80 meters, but that's a non-issue at this point, okay? If you want to have fun with the mathematics, just look at the website sometime, or this on YouTube. That'll be great. All right. So, but for the purist, okay, and is there a little bit of improvement? Yeah, a little bit, you know. You're splitting hairs. I use magnet mounts all the time. I'm selective about it. I'll tell you, the diamond animal magnet mount is SPM is excellent. But you know, here we have two ways: the obvious through hole mount, and you can see it's near a corner. That's great. And here we have, there's all kinds of mounts for vehicles these days. This is an adjustable mount with screws going right into the body. So here we have on the SUV crossover hatchback near an upper corner, again, near the corner. You know, that's the best for your, especially VHF, SWR, and performance. So these are more permanent mounts. Here we have an example of both antennas on the vehicle, one near one corner, one near another corner. This one to a ham radio transceiver, and this one to a scanner radio receiver, or GMRS. What about the use as a base station? Because, you know, we have HOAs, we have other people living with us. They may not like the large antennas. Can this diversity help? Absolutely. Notice I say, especially if you're below 100 to 150 feet above the ground or height above average terrain. Well, how many of us have chimney mount installations or peak of our roof installations, or even tower that's less than 100 to 150 foot? Well, the vast majority of us, actually. So that's where you benefit from not just real long antennas and high gain. But if you're at these kind of elevations, you very much benefit from the broad pattern and the diverse electromagnetic field. So these are base station adapter kits. There are various manufacturers. They're available from the resellers, and the best thing to do is take them, easily done in a vise, probably even with a couple of pairs of pliers, but easily in a vise. Bend the radial down to about 70 degrees below the horizon, and that's the most effective way. Beautiful SWR on all the different bands. So this could go, you know, up on the roof. It looks like a little vent pipe, hardly visible, or in the attic, for example. So is it real? All of that, does it wind up having, really, does it have good SWRs? And what's the Smith chart? You know, what does that show in terms of how far does it deviate on the inductance side and the capacitance side of the Smith chart? Well, it's pretty good. Now, this is on an HP Agilent RF network analyzer. That's not a $50 VNA. That's more like a $50,000 device. And here, this is both for base station as well as mobile. You can see you have some very, very nice SWRs. This is near the corner or on the base station. On all, this is 2 meters, 220, 440 right around here. We have a little bit of coax effect there, as you're all familiar with. Here's the Smith chart. There's your immediate spot right there for 50 ohms with no inductance and no capacitance. And there it is right there. And it hovers around there at 2 meters, hovers around it very closely at 220, and it circles around it at, but in close proximity to the 50 ohm pure resistive point. What are people saying about it? Check my time. Actually, I turned my phone off so I wouldn't be disturbed. Does somebody have the time? Oh.
It's 7:44.
7:44. Okay, not too bad. All right, let's continue to move along. All right. So what are people saying about this? Does it really work? This is an article was written, editorial review by Bob Grove. What a great man, right? He's an icon in the industry. And he says the prediction of signal flutter reduction was true as well. When annoying flutter interrupted reception of weak signals on the whip, reception was much smoother with the COMPACtenna. I won't read all of this. This is about the 2 meter tri-band, 7.5 inch antenna. John was so excited. You can see it in his words. He says, well, I had to leave out a couple of words here. Not sure what sort of blank magic wizardry you've pulled off here, but the performance is fantastic on all bands right out of the box. And some of the customers comparing it with the Lairds and the Larsons and all of that, and just in the Diamonds, and just being extremely excited about it. They were hoping for just, you know, reasonable performance, and allowed them to do all the things they do, but it did much more than that. This is about the Scan 3 antenna. Boom goes the dynamite. This is a nice review of somebody that used it for scan or receive at various bands. Okay, so that's VHF, UHF. That's half the, in a way, structurally anyway, well, yeah, of the antenna line. Now we go to the HF. I'll pause for a moment in case somebody wants to say something. I can actually hear a little bit of audio in the background. Somebody might have their audio not muted. Sounds like a radio or something. Can you hear that, Lloyd?
No, I guess if I listen real carefully, let me see if we'll find out who's not muted. We have several people with us that haven't muted their mics.
It's gone now.
Okay.
Okay. All right. I'll move on. Let's go to HF. Okay. Let's start with shortwave receiving. we have a 20-inch antenna. That's right, it's only 20 inches long. And it has a 3/8 24 CV style, you know, and here it is on a Hustler MBM Magnum mount, a very good Magnum mount. Here, not to say there aren't others that are good, but I happen to have a lot of people have great experience with it. And it's on a metal sheet, and it's in a closet here right now. You know, again, HOAs, condos, apartments, homes, etc. It's great to. Looks like I did something here with the screen. Oh, there it goes. Okay. So what size metal is needed? All right. Well, let me tell you, you remember that slide where I did the calculations on the Magnum mount and the capacitive coupling between the Magnum mount and extremely close to the metal? Well, this metal counterpoise has capacitive coupling to earth and groundwater. Okay. So clearly, it couldn't stand alone, right? Because you would think you would need radials. It's nice to have a short antenna, a small antenna, but if you have to have radials that are going out in whatever, 25, 40 feet length all around, well, that makes things a little more difficult, doesn't it? So that's what's going on in this case, all right? Now it is beneficial to use several RF ferrite beads here along the coaxial line, because depending on whether you're on the ground floor or the ground, you know, or 8 feet above the ground, 16 feet above the ground, or 24 feet above the ground, say if you're in the second floor attic and you have a basement, you know, your capacitive coupling decreases. So therefore, your effect on the SWR, but of course this is HF receive, not as significant, but also your common mode situation changes somewhat. So therefore it's always a good idea, and that's the best place location for them for the RF beads. Several of them, clamp on, for example, styles. So how large? This is a standard 3 foot by 4 foot sheet that comes from home improvement stores. It's roofing flashing sheet. It's galvanized metal. You know, they in hardware stores also sell 2 foot by 3 foot sheets. You can overlap the two of them, making about 3 foot by 3 foot, and that's okay too. Caution with the corners, they're sharp. I recommend filing, sanding, rounding of the corners, duct tape all around. How does it work? This gentleman used it on both a Yaesu as well as a Texan shortwave receiver, and you can see he loved it. Here it is in the attic, same kind of thing. All right. Now, on my website, the homepage, there's this very enthusiastic gentleman that does de-expeditions with shortwave for Delta 65, and he's tested a lot of antennas, and he really likes this one. Now note this, model SW is not recommended for vehicles in motion. You know, it's short, but there's a pretty good wind load on there. So but for de-expeditions, POTAs, essentially for receive, absolutely. So anyway, there's some really neat video clips and YouTube video clips on my site of Redelva 65 using this antenna, and other video clips as well of the shortwave antenna. It's a little fun to watch. They're short. Let's then move on. We're coming to the end here because this next slide has a lot on it. Let's go to HF ham radio, two-way radio communication, CV, and also shortwave. So for two-way communication, the preferred method is this. Remember I talked about the capacitive coupling. So ideally you have it on the ground. Now you're dealing with very short antennas here. And in fact, as it says here, you can actually bury this under the ground, the soil or the mulch a little bit, as long as the feed point is up above the ground. You talk about invisible, that's pretty invisible. You can use a magnet mount, of course, on a galvanized sheet. You could use a heavy duty through hole mount, because you know, you have something to work with on the underside. You have soil or grass, mulch, whatever the case may be. In that case, if you use these, you can use a galvanized sheet, or you could use aluminum sheeting, for example. The thickness only of the sheeting only changes the structural integrity, really. It doesn't change the RF properties substantially. So there are various 20-inch models, and they're inexpensive. USA made entirely, but inexpensive. There's the 20-meter model that also covers the 2-meter and 440 band. There's the 10-meter, 2-meter 440, 6-meter, 2-meter 440, CB, 2-meter 440, and of course the shortwave, as I already discussed. 20 inches tall, believe it or not, surprising. Look at my homepage. It was a field day, people talking all around the country in Canada, and that's when we were in the null of the cycle, or the other side of the null, with the 20-meter, 20-inch antenna. When I first introduced this, it's like every time in my life, I come up with a new concept, you know, one that winds up being on every Secret Service vehicle in the country, you know, hundreds, thousands of them in Washington, D.C. for Homeland Secret communication, a different patent because it worked better than full-size antennas in the obstructed environment. You know, each side, they're naysayers, and they're very funny, but not so much anymore. Beginning to find that with this magnetic field resonator, it actually works. 20-inch, 20 meters. Here's the Hammer 7. Now this is the one that covers all these bands. That's why it's a 7. Now this from up there to the bottom is 46 inches, and it can be used likewise. It's a little bit more costly, but less than other technologies that are out there actually. You know, such as magnetic loops that I'd love to talk on more, but let's not do that today. But be that as it may, and much shorter than your typical shortened whip, multi-band whip HF antennas, much shorter. All right, so, oh, this is, I always include this, you know, I mean, most of us know this, of course. Notice the RF ferrite beads here, same thing. Don't touch any part of the antenna structure, mounting system, counterpoise, feed line while transmitting, and look at the specific absorption rate calculations on COMPACtenna.com installs page. It boils down to a kind of rule of thumb of 15 feet away when you're doing about, you know, 50 watts of transmitting or something of that nature. This should be obvious, but I've thrown it in there. It should be obvious for anything. Okay. So what do we have to finish with? Oh, a neat little recent invention. So let's say you have the VHF UHF antenna on that ground plane counterpoise I talked about with the elements angled down 70 degrees below the horizon, and you have it in your attic and it's nice, or you have it on your rooftop and it's pretty invisible and it's nice. But, you know, being at low elevation, you really could use a little bit of gain. And let's say you even wanted to have the option, you know, let's say one antenna does off to actually get it up through the opening of attics. They're only 20 inch by 30 inch. How are you going to do that with a fully assembled antenna? Even small antennas that are available out there without this technology, you have to bring it in pieces up into the attic and assemble it up there. Couldn't you have a beam antenna, a micro beam for 2 meters that comes almost fully assembled, and fully assembled could fit up into that opening? Yes, now you do. It's the 2-meter micro beam. It's extremely small. And frankly, it also looks like that pipes up on the roof. But you see what I've done here? I've taken this and incorporated an optimized full wave loop, optimized dimension, optimized spacing, in order to actually get 7 dBi gain out of an antenna that's only 19 inches long. And that's from this tip to back there. That's all it is. And 28 inches wide and 28 inches high. You know, a typical, you know, say 3 or 4 element standard single polarized beam is going to be on the order of 4 feet tall, 4 feet long, you know, much larger overall than this, much larger. So it does all of these things. It has a short length, short height, reduced torque. You don't need an expensive rotor. You can use a standard TV style antenna rotor. It's very convenient. It has a lot of applications, and it gives you Gives you good gain. And of course, front to back, that's just as important in communication, especially with all the noise. Switching power supplies. It's not just fluorescent lights and TVs anymore. It's all the switching power supplies. I have a virtual dissertation about that on my website, the installs page, and how to tackle some of those problems that people have. And it's even on 2 meter. By the way, one of them is your Wi-Fi router. Put some RF feeds on there. Check my my website on that. A lot of people don't realize it can get quite a bit of noise. Sometimes there's noise and you don't see it as S meter deflection because it's front end overload, it's desensing. But sometimes you'll actually see it. And Wi-Fi routers are really bad about that. It's not just the switching power supply of the router; it's the router itself. So you put beads on both. Anyway, so front to back ratio is really good, not just to knock off interfering signals, QRM, but QR Nancy, noise from switching power supplies and that kind of a thing. All right. And again, San Antonio Amateur Radio Club, thank you so much for this opportunity. I hope you have enjoyed the presentation. I really would like to answer some questions, and perhaps we could go back to video, or if somebody first calls on me to go back to a certain slide, maybe we should do that first and then go back to group video so we can see each other. We can't do it in person, but at least we can see it in video. But thank you specifically, Rosenda, President, Lloyd, Vice President, and Bill for all you're doing.
Well, thank